Arguments with quantified statements. If a property is true for everything in a set, then it is true for any particular thing in that set. So, for example, all men are mortal. Socrates is a man. Therefore, Socrates is mortal. So, the set of all men are mortal. So, an individual member of that set is going to be mortal as well. So, if a property is true for everything in a set, then it is true for any particular thing in that set. Let's see here. Simplify. R to the k plus 1 times r. We know that x to the m times x to the n equals x to the m plus n, right? And we know x to the 1 is equal to x. So we can show that this here is r to the k plus 1 times r to the 1 because of the second thing that we know. And then from this one we have r to the k plus 1 plus 1, or r equal it's equal to r to the k plus 2. So that's we use this sort of thing all the time in math, but like I said at the beginning of the semester, this is mathematically formalizing common sense. You know, if it's true for everything in the set, then it's true for any particular thing in the set. Just a little bit of common sense. All right, let's see here. Universal modus ponens. All right. So for all x, if p of x, then q of x is true. And then we know that p of x is true for a particular x. Therefore, q of x. It's just the same principle as the modus ponens that we learned before, just with a universal quantifier. If p of x, then q of x. P of a, P of a, I'm sorry. Let's see here. P of a for a particular a, then q of a. So that would be the formal version of modus ponens. The informal version would be if x makes p of x true, then x makes q of x is true. It makes q of x true. And a makes p of x true, then a makes q of x true. So got a couple examples here, it looks like. Using quantifiers, variables, and predicate symbols, write the following argument. If an integer is even, then its square is even. K is a particular integer that is even, therefore k squared is even. So, for all x element of z, if z is even, or if x is even, then square is even. So we would have even k, therefore square of k is even. Okay. All right, okay, let's see here. Another example. For all integers x, for all x, integer x, x is even if and only if there exists an integer k such that x equals 2k. Prove that if two even integers m and n are added together, the result is an even number. So, so we have this. So m is even. Therefore, m equals 2r, for example. 2 of the integer of some integer r. The same logic applies to n. If it is an integer, then it is a real number. All right, let's see here. Let's see here. Let's clear that. It's like, okay, if x is an element of z, then x is an element of r, right? And r and s are, let's rewrite this here. R element of z, s is an element of z. Therefore, r and s are elements of r. Okay? So, and we know the distributive property that applies to all real numbers. Let's see here. If A, B, and C elements of real, then A, B plus A, C equals A, B plus C. Distributive property, distributive law. Two, R, and S are elements of R. Therefore, 2R plus 2S equals 2R plus S. We also know that for U and V, element of integer, then U plus V is an element of integers. R and S are integers. Are integers. Therefore, R, that's right. R and S are integers. R plus S is an element of integers. So, going back to the original page there, if a number equals twice some integer, then that number is even. If x is even, then x equals 2 k, where k is the element of integers. Two r plus s equals 2 times some integer. Therefore, 2 times r s plus s is an element, is even. Therefore, and that 2 r plus s equals m plus n. Therefore, m plus n is even. Kind of a long, drawn-out, formalized version of an argument that you might have had in a process you might have seen in Algebra 1 or Algebra 2, but this, again, formalizes it. Yeah. It's using modus ponens. If x is even, x is equal to 2k, where k is some element of z. 2 times r plus s equals 2 times some integer. Therefore, 2 times r plus s is even. It's modus ponens, but with the universal quantifier, it shows that if x is true for all elements of the set, even integers, and one particular integer makes it is a member of that set, then that is I'm sorry. Yeah, it's a universal modus ponens. Then we also have the universal modus tollens. Well, where for all x, p of x implies q of x, and not q of a, therefore not p of a. If x makes p of x true, then x makes q of x true. A does not make q of x true, therefore A does not make p of x true. That's modus tollens with the universal quantifier. Let's see here. Let's say all humans are mortal. Zeus is not mortal. Therefore, Zeus is not human. So, what is the conclusion of the following argument? All professors are absent-minded. Tom Hutchins is not absent-minded. Therefore, he's not a professor. I think that's a job requirement. Not sure yet. Okay. Proving validity of arguments with quantified statements. I think we've gone through this one before, but it deserves saying again. To say that an argument form is valid means the following. No matter what particular predicates are substituted for the predicate symbols in its premises, if the resulting premise statements are all true, then the conclusion is also true. An argument is called valid if and only if its form is valid. It is called sound if and only if its form is valid and its premises are true. If you have a false premise, then the argument is not sound. I believe I think I read through that before, but one way to show validity of arguments is with diagrams. Let's see here. Let's do the all integers are rational numbers. Integers. So you can see when you make an argument about integers, rational numbers are partially included. When you make an argument about rational numbers, integers are included. Now you can have use two here. See, mortals and humans from the previous example, and then separate from that, you have mortals and Zeus. Zeus is outside the group of mortals. If Zeus is outside the group of the set of mortals, and humans are all within the set of immortals, then obviously Zeus cannot be human. Now, you could also show invalidity. Let's see here. Let's continue with the mortals. Humans. So all humans are mortals. And then that's the major premise. And then the minor premise is that Felix is mortal. Therefore, Felix is a human being. Is that valid? Mm-mm. If you combine these two, you could have mortals humans, and Felix right here. So so in this case, it's not a valid argument. That's trying to use modus ponens when it doesn't apply. See, this is going. Let's see here. Well, yeah. You're trying to apply universal modus ponens, but it doesn't apply because you're not showing if X is a human, X is then X is mortal. You're doing the Q trying to prove P instead of P trying to prove Q. Because after all, we all know Felix was a cat, right? The old cartoon. Are you guys too young for that one? I was on when I was a kid. But no, Felix could be a human being. You know, it has two possibilities. Both are valid possibilities given the information. But this is an example of converse error. It is not a valid form of, and it does not lead to a valid conclusion. Inverse error would be if the formal version would be for all x, if p of x, then q of x, and not p of a for a particular a, then not q. Or the informal version, if x makes p of x true, and then x makes q of x true, a does not make p of x true, therefore a does not make q true. That is also an invalid conclusion. That is inverse error. All right, let's see here. Use another diagram here. Test the following argument for validity. No polynomial functions have horizontal asymptotes. So, polynomial equations. And then functions with horizontal asymptotes. My spelling might be off on that. Ooh, I got it right. I think, yeah, I did. This function has a horizontal asymptote. So this function. Therefore, this function is not a polynomial function because there is no intersection between these two sets. Therefore, it is a valid conclusion. This function is not a polynomial function. Other additional forms of argument that are available to you include universal transitivity, where for all x, p of x, q of x implies q of x, and for all x, q of x implies r of x. Therefore, for all x, p of x implies r of x. The transitivity law applied to universal quantifiers. And a little remark on converse and inverse errors. One reason why so many people make converse and inverse errors is that the forms of the resulting arguments would be valid if the major premise were a biconditional rather than a simple conditional. Consider, all the town's criminals frequent the den of iniquity bar. John frequents the den of iniquity bar. Therefore, John is one of the town criminals. Not a valid conclusion. But if it were a biconditional where only people that go to the den of iniquity bar are criminals, then it would be a valid conclusion if John frequents the bar of iniquity, den of iniquity. Now, converse error can be useful, provided it is used with caution. So, let's take example, okay, for all of x, P implies P of x implies Q of x. Or if P of x, then Q of x. And Q of x is true, therefore P of x is possible. So car mechanics and doctors use this to diagnose problems in cars and people respectively. For example, you complain about your car pulling to the right. If your car pulls to the right, or no, if you have a bad front end alignment, then the car will pull to the right. Car's pulling to the right, so it's possible that you need a front end alignment. There are other possibilities. Your front right tire might be low on air, and that would cause you to pull to the right as well. But it narrows down for the doctor or mechanic what could possibly be wrong. So P of x is not necessarily true, but it is possible. Check it. Ask for more information, get more specific, and it can lead you in the right direction. If you have pneumonia, you have coughing and fever and chills and all that sort of stuff. Somebody comes in with severe coughing and fever and chills and all that sort of stuff. One possibility is pneumonia. Another possibility would be COVID. But narrows down the possibility. Come in with those symptoms. It's not going to be a brain aneurysm. It's it helps narrow down the possibilities so you can find do further testing to determine what the problem actually is. And that, I believe, is it for chapter 3. Since we have 35 minutes or so left on the clock, is there any questions? Are there any questions that you might have about chapter 3? Where does chapter 3 begin? We're going to have a review session on Tuesday, and then the midterm on Thursday. So homework is due before class on Monday. Of course, as with all previous examinations, open notes, printed notes, have them on a computer, print them out, have them on paper. There's not going to be an opportunity to make up the midterm before midterm grades come out, because midterm grades are supposed to be submitted the following Monday by 5. So there's not a whole lot of time to do any makeups. So be here for that. Anybody watching the video should get that message as well, as we don't have that many people in here today. Yeah.
This one on the homework, it's okay to email you like you said?
I believe I gave like 3 or 4 chances. Yeah. on the
I haven't started.
oh yeah, I believe it's 3 or 4 chances on each question. But I guess we'll call it an early day. Have a good day. Have a good weekend. Enjoy Friday off. No classes tomorrow. So see you on Tuesday.